All right. Can you hear me? Oh my goodness. Hey man, can you hear me?
Yeah.
Okay. Yeah, it usually boots you out when I do that.
Okay.
All right. So how are you today?
Yeah, doing okay. I'm just trying to work on some like the lab for
Okay.
tomorrow,
Okay.
the PChem.
Uh, is the T10 due tomorrow by chance?
T10 is due, I think, tomorrow. Yeah, let me check.
Okay. I guess I can get you the exercises for that, just to
Let's see
like
if we'll
talk about it
schedule.
on Thursday.
Okay, let's see. Okay, it's T9 that's due tomorrow.
Okay, really? Oh, that's good. I guess I'll do T10 like after homework 6.
Okay.
Okay. How did you do on the? Did you guys get the? Oh wait, T9 is due tomorrow. Okay, so you don't have the
Yeah,
solutions yet.
not
How
yet.
how are how are you doing with the CTQs?
Um, I mean, for the most part, okay, but it kind of got a really, I guess, intense at some parts.
Oh, really? Okay. I wasn't like I don't know if I have the actual questions.
Yeah.
You want to just show me? I don't know if you have them like on your computer.
No, I don't. They're kind of on the
Okay.
screen. Um, Not on the
No,
screen, but on my not no photos. I don't have any or anything. I'd have to take
I
photos
guess
of it. I don't have a PDF.
yeah. What we can do is probably if you I can help you out with that if you take a picture and then maybe send that to me tonight. I
Okay.
can help you out. But then which questions though? Like in general, like what about it?
So let's see. I guess whenever you have like because they're talking about like DS, which I mean
Okay.
that should be that's entropy. Um,
Yes, entropy. Yeah.
they're asking when is that DS change of entropy equal to the change in, I guess, heat because it's Q over T.
Yeah.
So because I know it's if it's great if DS is greater than dQ over T, it's spontaneous and reversible.
We know that one.
Um,
Yeah, that's actually one of the ones that's in this exercise, which is good because it helps you. It help like the ones in the exercise are really good questions because it's very conceptual in
okay,
this sense, which may appear like in your exam. For
yeah,
this one, it was weird because as I saw from like the other exercises, it wasn't very theoretical, but this one was.
yeah. So since I know that if it's greater than dq over t, it's spontaneous and reversible, but if it's equal,
It's equilibrium, yeah.
then
For G or S, which one are you talking about?
for
G.
ds equals dq over t.
Oh, when it's equal to 0,
No, when it's just when ds is equal to dq over
DS.
t.
That's just the entropy itself. Like that's the dq over t. That's the second law.
Yeah, so does that mean since they're equal, then they're spontaneous and reversible conditions?
I believe so. I remember like when ds is like it's if it's less than, that's like
It,
irreversible,
yeah, it won't happen.
and then if it's like 0, that's reversible or equilibrium.
Okay.
If it's equal, but then if it's dq over t, is that like is that question conceptual or is it like solve it?
It's conceptual. So because I know that if ds is greater than or equal to dq over t, it's spontaneous and reversible. As well as if ds is greater than dq over t. But if it's equal, because like greater than or equal to is two parts, so
Yeah.
would it still pretty much be the same reasoning?
Yeah, it would be the same reason.
Okay.
I'll give you like the full reasoning later on. Typically when it's the form of it is either greater than or equal to, right? I think we defined this last time. If it's and if it's equal to, it means that it's in equilibrium. Same thing, you know. And then if it's what's it called? If it's equal to, it's reversible, a constant. And if it's greater than, it's reversible, and then it will increase, something like that.
Yeah, so spontaneous, I guess. So if something spontaneous, what kind of condition would it be? High
Spon-
temperature or
Spontaneous is like natural events, right? Like something irreversible, spontaneous.
yes, I guess just anything that happens naturally.
Yeah, that's
So
spontaneous.
that's so condition wise, how would I like define that? So just normal conditions or
Normal conditions, yeah.
okay.
Something that will obviously be natural and normal. Yeah, I wouldn't call like something that can't happen, like going from maybe ice to or like liquid to ice, like in like a hot day, something like that. Like just put in like an example that can't happen in reality, or like can happen, and then like tell them that if this can happen and this, because your DS itself will tell you if it's less than, that means that it can't happen, and if it's like greater than or equal to, then that means that like that's an event that can occur. And if it's like greater than, you can tell them it's a spontaneous thing. But then if it's equal to, then it's that process can be reversed, right? Something that can be reversed can be like phase changes can be reversed depending on the
Okay.
condition.
So the only difference between greater than and equal to is greater than means it's just spontaneous but not reversible. Only if it's equal.
If yeah, that's what it is. Like if it's greater than, it's irreversible or spontaneous, and then if it's equal to, it's reversible and it's non-spontaneous.
Oh, non-spontaneous and reversible?
Yeah, reversible is I believe so. Yeah, it's like reversible is equilibrium, and let me look back to this one. Just the definition is just so I know what I'm trying to say. Entropy science. Okay, let's see. We did this one in TA. I don't have that one here, but like usually when it's greater than or equal to, let's the entropy A. Oh, here, yeah. So if the entropy is negative, that means like it's spontaneous. If it's positive, that means the reaction is non-spontaneous, and it's a reversible process. That's usually how I know it.
Hmm.
Yeah, if it's non-spontaneous, that means it's reversible.
Okay, because apparently it says spontaneous and reversible,
Where
both.
does it say? Where does it say that one?
Um,
Is that like in the chapter?
yeah, but I mean that's what he was explaining on in lecture. Let me
It really
see.
depends on the sign, like the sign of S.
Yeah, ds is greater than dq over t, greater than or equal to.
So what is non-spontaneous then? Less than. That's what it's saying.
I
Is that what?
guess I guess so. It just says ds is less than dq over t. It won't occur. That's all I got on here. Um,
So if it's greater than or equal to, yeah. If it's greater than or equal to, and if it's non-spontaneous, that means it can't happen. So it's not natural. Yeah, you could say it that way. I've seen it before where it's like if it's spontaneous and irreversible, then that's usually the one where it's like greater than, and if it's like equal to zero, that's when it's equilibrium and reversible, but non-spontaneous. But like if he defines it as that, non-spontaneous would then be the one of natural, which is like less than, right? Less than would be non-spontaneous.
Yeah, less than should be non-spontaneous, I guess then. Okay, so I have to change my answer.
Because you need to have those three. You need to have something that's spontaneous, irreversible, equilibrium, reversible.
What do I need? I am
Like you need to like for all of those. Like if you have the entropy term and you have like an H term enthalpy, or you have Gibbs free energy, or you have like Helmholtz, all of those tell you something about the process. If they're spontaneous, or if they're irreversible, and if they're like you know, like in equilibrium, they tell you all of that. Like because those are like the four different. I think S, H, G, and A are like the four different thermodynamic properties. They're like the main ones. But like just in terms of the question, for you know, just talk about the delta S obviously, or like ds.
okay. So if ds is equal to dq over t, it is non-spontaneous.
Yeah, and then let's put it as like equilibrium and reversible.
Okay, what are the differences between those three? Because there's spontaneous, there's whether it's spontaneous or non-spontaneous, irreversible, reversible, and equilibrium, non-equilibrium. What are the differences between the three?
Okay, so they're all like you know they're all synonymous. In essence, this is what I'm talking about. If do you see my screen?
Let me see again. Yeah.
Okay, so like for example, this one is about the Helmholtz one, the A term. The A term tells you if something is non-spontaneous, which is like a non-spontaneous event would be something that doesn't naturally occur. So, and then like if you have a spontaneous event, that's something that can occur. And then for the most part, when something is spontaneous, it's also irreversible. So that's like the same thing. Like if something is spontaneous, it's also irreversible. It's an event that doesn't happen like you know uh, irreversibly. And then if an equilibrium, equilibrium means like usually it's associated with zero. If something is equal to zero, that's equilibrium. At the same time, because it's balanced, you know, like when something in statics, right? If something is equal to zero, that usually means that like it balances to zero. That's why it's reversible, because like, it just balances. And irreversible, it's an inequality. It's an inequality, right? So an inequality means like you cannot go one way or the other. It doesn't balance out. But for like a reversible process, it balances out. That's why it's a reversible process, and that's why that's an equilibrium.
I don't know. I don't know why I don't understand the definitions very
It's really
much.
it's really just like if something is in equilibrium, like in statics, everything that's in equilibrium goes down to zero, right?
What do you mean goes down to zero?
So like F equals ma. This is like Newton's law, right? F equals ma.
Okay.
F equals zero. That's equilibrium. That's kind of like what's happening here. So this is a balance equation. It's conserved, right? Like your forces, like
So
this force.
there's no force.
There is a force, like internal force, but the if you add like this guy and then this guy, P, there is a force, right? There's a P
Mm-hmm.
force and there's a Q force, but altogether they should balance out to zero.
Okay.
So P plus Q. So Q in this case, two things can happen. Q can either be negative P or P can be negative Q plus Q. So there's forces in here. There's forces in here which balance out, and that's why they're in equilibrium because they're conserved. Equilibrium, like the what does F equals ma do? Like it's in rigid body, right? You have rigid body motion. Things are moving. So that when you do F equals ma, things are not moving. Same way with the phase change. Like you have a lot of energy away from the phase change, right? Let's talk about like maybe like the Gibbs form, like the Gibbs free energy. Gibbs free energy. You know, if you're at like when you're changing from like solid to liquid at that phase change, your Gibbs free energy is 0 because you're not emitting anything, right? That's when it finally your energy is finally changing, and you're at that balance point. It's the same thing as F equals ma.
So is it net force, not just force? It's just net force.
Yeah, that's net force. Like, but if you take a look at this guy, a P or a Q force, essentially there's forces within the body, but like altogether they should equal 0, and that's why it's like it's an equilibrium because the whole body isn't moving.
Mm-hmm.
But then if you have F equals ma, which is kind of, it's not an equilibrium. F equals ma is kind of like this guy. It's not equal to, you know, it's not 0. It's a spontaneous. And then when you're moving, right? When you're moving one way, you can't really move back to the other way, right? So that's like it's irreversible.
Hmm.
It's just a definition thing. A lot of these guys, like for example, like E2, when you have to remember, like when the Gibbs formula is less than 0, it's the same thing as saying, what is the Gibbs formula when it's less than 0? What does that mean? It's spontaneous and it's irreversible, right?
I don't know.
Okay, yeah, these definitions are just pretty much what it is. Like if it's you have to like, right now, it doesn't sink in, but if you have a delta G less than 0, that's what it means. It's the same thing as this guy. Let's say spontaneous, irreversible. It's the same thing as this guy.
Okay.
These are just definitions. Like when you want to talk about something, you have to define what that means, right? Like these are just definitions, and then you use this to kind of explain what's going on. But you have to remember like what their signs are. Like at equilibrium, the Helmholtz equals 0, and then at the same time, the Gibbs free energy is also 0. So that it builds kind of like that repertoire, you know, like the thermodynamics repertoire is like, oh, when something is in equilibrium, then we can assume that delta G equals 0. When someone says equilibrium, they don't have to say delta G equals 0. And when someone says like, this is another thing as well, if you have like an exothermic reaction, something is giving out heat, giving off heat, someone doesn't have to tell you that delta G is less than 0. They just have to tell you that it's exothermic, exorganic or exothermic reaction. And if something is absorbing heat, that's an endothermic reaction, right? So when something is being like a heat is being absorbed, that's layman's terms. Someone can just say, yeah, like this process is absorbing heat. So because of that, you can say that the Gibbs free energy is greater than 0. Let's kind of like define what that means though, like, you know, in terms of like what is delta G equals 0.
Okay, so if it's greater than 0,
If it's greater than 0, it means it's endothermic for delta G. Or which
okay,
one?
and I mean, I'm just thinking like less than 0, equal to 0, greater than 0.
Yeah, those are the only 3 things you have to for like G, A, S, and H. Those are the only things you have to remember.
G,
And
A.
S, you know, like, and you have to have those like concrete. You know, when delta. I think the delta S we covered that last time, and delta H. I can reiterate those again for delta S and delta G. signs of like entropy and enthalpy? Because they're gonna ask you that, like those types of events. Like what does a if you have like a the like for example for this exercise one, this is a pretty common one when like there's a phase change. That means it's in equilibrium. If it's in equilibrium, if delta G equals 0, delta H is also equals 0.
And so is delta
Del
S and
yeah,
delta A as well. All four.
hold on, let me rewrite it. Oh, delta A is 0. No, like what's the equation again for this guy? G equals, what's the full equation for G? Gibbs free energy.
T delta S or
Let me look back to it.
T minus delta S or something.
H minus TS.
H minus TS.
So it's delta H in like differential term delta S. So if he tells you, or like if anyone tells you that there's a phase change, you can always assume that this is 0, and then now you can solve for these guys. These are not always 0. These guys.
Hold on. Okay, so I'm just trying to just not looking at examples. I'm just trying to understand definition wise. So for which one of those four G, A, S, and H is, if it's negative, less than 0, it's spontaneous and irreversible.
Oh, so you want to know their signs when it's spontaneous and irreversible?
Yeah, for each of them.
Okay. So let's write that down. So spontaneous and irreversible. Okay, let's see what they are. So the ones that can tell you what they are is this guy. The delta G is one of them that can tell you if it's spontaneous or irreversible. Is going to be less than 0.
Okay, hold on. So, because I was just thinking, because for each of these, like for each case, I mean, I know that it just depends on which one is applicable to what, but for just in general for these four, will the relationship between like less than 0, equal to 0, greater than 0, will it always be the same for spontaneous? I don't know. Spontaneous, irreversible. So spontaneous and irreversible is always going to be for greater than 0, or I mean less than 0.
Less than 0, yeah. For G, always for G and A, yeah.
For G and A, okay. So G and A. So for less than 0, okay. And then I know that equilibrium and reversible is going to be equal to 0. And which ones are those going to be?
So that one is really simple one. That one is just all of them, right? This
all
guy.
Of them?
Yeah, and then this guy. These two are the ones that usually you can assume, delta G and delta A. The other ones are like for delta S, as I remember. Let me see this one. As the delta S. Entropy. Okay, so for spontaneous, delta S is greater than 0. And then
okay, so sometimes spontaneous and irreversible can be greater than 0 too?
Spontaneous and irreversible, yeah. For delta S though, because delta S can't, when it's less than 0, what is that? That's non-spontaneous, right? Or that can't even happen. That can't even happen, I think. It's just because delta S has to be like greater than or equal to 0.
Okay. And then anything else for spontaneous and irreversible greater than 0?
So you have this G, A, and S. Usually H is the one that doesn't really tell you what that is, like H. H, H is enthalpy, right? We know that one, right?
Yeah.
And enthalpy, that's not something you assess if it's spontaneous or irreversible. The thing that enthalpy, the H, tells you if it's like endothermic or exothermic. Have you? It doesn't tell you if something is, spontaneous or irreversible.
Okay.
It's usually just these three.
Just those two. Okay. But it can still say if it's in equilibrium or not.
If it's equilibrium, it's an easy one because all of them equal 0.
Okay, so delta H is 0 as an equilibrium too.
Delta H is not the one that you can't use delta H for that. Delta H just tells you if something is absorbing heat or releasing.
Okay.
It's only
So
these three.
it's not for all four for equilibrium equal to 0. It's just G, A, and S.
Yeah, gas.
Okay. So we have spontaneous and irreversible. What would be the opposite of that? So like I know G and A. So would that, if it was positive, that would be non-spontaneous and reversible?
So non-spontaneous.
Because I know there's another
So
relationship.
non-spontaneous would be for delta G, which is like greater than 0. So delta G is greater than 0. And delta A is non-spontaneous. Delta A is greater than 0.
Okay.
And then delta S is less than 0. And then
Wait, delta, I thought delta S was greater than 0.
For which one?
For
Reversible. This is reversible, non-spontaneous.
okay, I just remember you mentioned delta S, for what's greater than 0 is delta S.
This guy, if it's spontaneous and irreversible, delta S is greater than 0.
Okay.
If it's in equilibrium, it's equal 0 for delta S.
Okay.
This spontaneous and reversible are not really, for the most part, the ones that are like interchangeable are equilibrium. Whatever I slashed here, this is the one. This is a third one right here. So spontaneous equal irreversible, equilibrium equals reversible.
Non-spontaneous equals equilibrium equals reversible.
Equilibrium is reversible, and then spontaneous processes are irreversible. Yeah, they're usually interchangeable.
Okay. Equilibrium is equal to reversible. Spontaneous is equal to irreversible. Are those opposites?
Which one?
Like the two on the left.
What are they? You're talking about spontaneous and irreversible?
Spontaneous and irreversible versus equilibrium and reversible. Are those opposites?
I wouldn't really call them opposites, because like when you're saying opposites, then you're accounting for like positive numbers, right? Because then every time like when you're saying equilibrium, I would put it I would put it as like another category. And anytime that something is in equilibrium, usually it just means that parameter is 0. I wouldn't call it an opposite. The opposite would be probably this guy, non-spontaneous.
Okay.
But I wouldn't say like that's why there's three. There's three things that can happen. There's three signs. There's three signs that you have to remember with like these thermodynamic parameters.
Okay. I gotta erase everything then.
And then there's another one. Let's just since we're talking about definitions, there's exothermic. You guys have already touched on this one. Exothermic, and then endothermic. Endothermic, and this is the only parameter here is H, delta H greater than 0. Which one is that one? Delta H, is that the one? Endothermic. And then also for this one, you have a delta G. Delta G tells you something else about these guys. Yeah, and yeah, it was the other one. It's this guy, and if it's absorbing heat, delta H is greater than 0. If it's absorbing, which is endo. And then delta G, if it's exothermic, is less than 0. Less than 0. Less than 0. Endothermic absorbing, delta G greater than 0.
Okay, how about endergonic and exergonic?
They're the same thing.
So it's the same.
Endergonic and endergonic and endothermic is the same thing. Yeah. Endothermic.
Endothermic is the same thing as endogonic, or how do you pronounce it or spell
Endergonic.
it? Ender and exer.
Yeah, versus endothermic. Exer, ender, exer.
So endergonic is the same thing as endothermic.
Refers to other change in free energy. Isn't it the same as endothermic? Yeah. Yep. It's the definition is not the same, but the ending is they're both absorbing heat. If it's endergonic and endothermic, the only reason why you're saying gonic is you're talking about the Gibbs free energy, and then when you're talking about like endothermic, you're talking about FLP.
Okay, so it's delta G versus delta H.
Yeah.
Okay.
However you spell this guy. I'm just gonna put the thermic, but just when you're talking about gonics, when it's saying gonic, exogonic, you're talking about G's.
Okay.
If you're talking about thermics, you're talking about H's.
Okay. Let me write that chart down then.
Yeah, for the most part, like after this class, these are the ones that will linger. You know, like what does it mean to have a spontaneous? What does it mean to be exothermic? It's like my delta H is negative. Every time you're absorbing heat, which is endothermic, your delta G and delta H are positive. And then you have to reflect on this. Like, is this reflective of nature? Like, it seems like when you're absorbing heat, the heat itself is increasing. So that's why your FLP is increasing. When you're releasing heat, the body, the system itself is getting cooler. So delta H, because delta H is usually synonymous with Q, right? The heat capacity.
Q. Also, I've noticed that you've been using 3 dashes instead of 2. Is that why
This one?
do?
This
Yeah,
one?
I was just wondering because I've also seen other professors use 3 instead of 2, and I'm wondering why.
Okay, that's a good question. So this means that like it's always equivalent, or sometimes when I say this, I just put like a word definition. Like this is what is A is Helmholtz, right?
Mm-hmm.
When I put A equals, I want it to be a number, like with two lines. When it's 3 lines, it's just a definition, or like it's like equivalent in all regard. When I do like equals with 2 lines, this just means I'm assigning it. This means assign.
Okay.
This
So
means like,
should I be changing how I write stuff so that when I'm writing definitions, I should be using 3 lines instead of 2?
yeah, I think you should do that one. I'm writing when you're writing definitions, you should
Mm-hmm.
use 3 lines.
Okay.
And when you're assigning values to variables, you should use 2 lines.
Okay. If I'm basically filling out an equation, plugging in values, should I still be using the triple line?
No, when
Um,
you're plugging in values, it's going to be the double line.
so like if I have, let's say, like PV equals nRT, um, whenever they write the formula, they don't use 3 lines sometimes. They just
For
write
which one?
2.
For
Like
which one?
for like an ideal gas law or something,
Yeah.
PV equals nRT,
Yeah.
they don't use 3 dashes, they use 2, even though it's a definition.
This is not really like this. These are plugged in. Yeah, you're plugging values for these guys. What I mean by definition is what is this guy? Pressure, right?
Hmm.
And this is what I mean by definition. This is volume.
Okay.
Like definition in terms of words.
Okay,
You know.
because in the textbook they're using G and then 3 dashes A plus PV when they're showing a definition.
A plus PV.
Yeah, they're using.
Oh, I see. I see where you're getting confused now. Okay, the way I'm using it is valid. The way they're using it is also valid. It just depends on like what you're trying to say. Like I said, like when you're doing like this kind of thing, you know, or
Mhm.
like PV equals nRT. It's that sometimes this can change, right? This can change. If you're doing like this triple, this just means that this is the definition. It's really like
It will never change.
it'll never change. It will change though. A can change. This can change, right?
Okay.
Volume can change. I wouldn't go to it like I wouldn't read into it like so much where like do you need to use 3 lines or 2 lines?
Yeah,
It's
it's
just
just I want to read into it because I want to make sure I'm not incorrectly
miswording it.
filling
Yeah.
whenever I like write papers and things. I don't want to use the wrong notation.
For me, like I said, this is when you're assigning like a
Uh-huh.
value, and then
Okay.
when you want to do this, you could either do this one of two ways. You could either do this with like word definitions, uh, or 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 like an equation that like it's like a F equals ma. You could have done this with F equals ma, right? It's like a law, you know,
Yeah.
an equation, a law, whatever. Maybe PV equals nRT is also one because
Okay. So
it's an ideal gas law, right?
so it can sometimes be used interchangeably.
This guy. Th- I've never seen this guy like I've never seen something equal and then you put like this is you put words, this is Helmholtz.
Yeah, I'm just like talking about whenever you use the 3 dashes, sometimes can you sometimes use 2 dashes instead of 3 dashes for something
That's-
that's given in 3 dashes? So,
Uh, this guy can be used kind of similar to this guy, but the thing is, it's not numeric. You don't want to be doing something numeric. You know, I don't think it's even interchangeable because this isn't. I've never seen it that way. It's usually when you're assigning like numerics to like a variable, it's usually
Mhm.
just 2 lines. If it's 3 lines, it's either a word definition or like an equation law.
Okay.
Yeah, this is good practice if you want to like be consistent.
Yeah.
Yeah, but that's the spiel of like that one.
So we could be given initially a law, and then when we work it out, we can then use instead of 3 dashes, 2 dashes and fill out the variables.
Yeah, like this guy, right? And then when you're given like this guy, this is also another mathematical law, right?
Uh-huh.
This is for all. This is what I usually do for like for all, like for given values. For example, if a is given to you as a number, I'm not gonna put units. You're gonna be using like an equal sign, and then this is given to you in like there's another one as well. And the arrow. I sometimes put an arrow. Like when I do this. So first I do this. So there's this guy. Like let's start out with this. Let's start out with the definition, and then the next thing I'm gonna do, I'm gonna plug in. This means to plug in.
Mm-hmm.
Like plug in a now. Plug in the values. Plug in the values, and then after you do that, I do like this conclusion thing.
That's like a therefore.
Yeah.
So
The reason the
what's the
reason
difference between the two?
the difference between the two, this guy and this guy.
Yeah, aside from them being flipped around.
So when it's like a triangle, an upside down triangle like this,
Mhm.
this means like since, and
Since,
then
okay.
and then this guy is therefore, or
Therefore.
like QED. QED is also another one. It's like one of those. But for me, the reason why, because I really work better with like mathematical constructs. Like
Yeah.
I don't like working with words because when you, I mean, but you have to learn that skill of like transforming the word problem to like a symbol, you know.
Yeah. I know that the E is an element. What is the, like when you're doing like vector analysis and stuff, sometimes they'll
Oh,
use a
oh
tiny
yes,
circle. So like it looks like a dot, an open dot,
an open dot,
like a
and
P dot Q. It's not like a dot product. It's like a
oh, you
small
mean
circle.
like this guy?
Yeah.
For the most part, like that's like an inner. I think it's like outer product. It's an outer product.
Outer. Okay.
An
And
inner
then an
product. An
inner
inner
is just
product
typical.
would be this one, a filled-in zero, yeah.
Okay.
And there's you haven't taken linear algebra yet, right?
No, but I'm just trying to be familiar with the terminology and the notations.
There's like dyadic product, inner product. You'll learn those.
Okay.
Yeah. There's even this guy, cross product.
Yeah, that's just a big X. And for a while, I used to use that as a multiplication. And so it
Yeah,
kind
this
of
gives you a
gets,
scalar, right? And this gives you like a
uh-huh,
vector.
and a vector.
Yeah.
Yes.
In like that's why I started doing that, because like when you're writing like when you take linear algebra,
Mm-hmm.
there's like so many different notations. You're gonna like kill yourself. Like what the
Yeah.
heck is going on? Like if something is bolded, if something is bolded, that just like that implies it's a vector, you know.
Mm-hmm.
If it's like not bolded, it implies that it's a scalar. Another way to imply a vector would be just to put this guy or like this guy, and if it's a scalar, it's just nothing. It's just that.
Okay. And I've also seen, this is, I'm just trying to remember because I'm thinking about all the terminology. I just really want to get it all out of my head. So I know a U is
Okay.
union. What about a upside down U?
Okay. That one is I think it's like an intersection.
Pop quiz. Okay, intersection.
Intersection and union. Which
Mhm.
one is which? I
Well,
think,
I know the regular U is a union, upside down U is intersection. I just need
this
to
is,
know what that upside down one was.
and then this guy is a union because it's a U.
Hmm. Yeah.
That's how you remember it.
And then del is an upside down. It's just a triangle, and then a delta is the, a normal triangle. So know that, and then that's just a Greek letter.
And there's like definitions for these. This one is a grad one, right? This is grad.
Gradient, yeah,
And this one is something else,
is
which is
delta
like it is delta, but then there's actually a definition for it. Like
really okay.
yeah, but like these terms you'll use them, and it's better to be acquainted with them so that like
Yeah.
when you're writing like equations. So I mean, right now that no one cares. Like it's most of like, do you know how to use it?
Hmm.
But later on, they're gonna be like, are you precise? You know, it's about being precise. That's why.
Yeah, definitely. And then the last one is that the only block letters that I know of are R as real numbers, but are there any other notations of different letters?
This guy, this guy is complex.
Complex, okay.
This guy is real.
Real. Mm-hmm.
I think there's this guy as well, which is like Laplace transform.
Laplace transform, okay.
And then what else is there? L, R, and then
I know
I mean,
there's one more at least.
which one is that one? The
I
F,
don't.
Fourier.
Fourier, okay. Okay.
There's this one. I
Probably
know
not.
these ones are always there. This
Okay.
one itself, Fourier transform. Fourier transform. There's a Fourier transform. Transform. Yeah.
Mm-hmm.
This is called Laplace transform. Usually they put this inside like a parentheses, and this one's a parentheses.
Yeah.
And then you have this integral one.
Mm-hmm. That's an integral. That's a partial.
Yeah.
Cool. Okay. Yeah, there's
So yeah.
a lot of terminology that I just want to have it all written down so when I see it, it doesn't confuse me.
Okay. So like I guess for chemistry, what do you have
I mean,
questions about these
this is
guys?
also kind of like math too. So
Yeah. In
so
essence, everything is math.
okay. So it's okay if you could go back up to the green definitions one more time. I'm just wrapping
Yes.
up how to write those.
Okay.
So
Let me
delta
just
G.
let me just delete these ones.
delta S is equal to 0. And then
exothermic, endothermic, and exo. What was the other one? Gurnic.
endergonic.
Yeah, and an endogurnic, and that one is just G. Just remember, there's a H here, and there's a G in the gon. So
yeah, okay.
Like usually when you apply these, it's just a word, like from a word problem or like a what is assessing what a delta G is. When you see these words, yeah, when you finally see these words, all this applies. All of these apply. Like it's for the most part, it's just do you know what to assume?
Mm-hmm. So endothermic. This is exergonic. That is delta H is greater than 0. Delta G is greater than 0. Okay.
Cool.
Okay. So ds is equal to dq over t, then it would be an equilibrium.
Yeah. dq over.
It's just equilibrium, not irreversible or reversible or anything. It's just an equilibrium.
It's an reversible. Equilibrium is reversible.
Okay, so
Equilibrium is usually reversible.
So spontaneous is irreversible, non-spontaneous is just that by itself, and equilibrium is equal to reversible.
Exactly. Yep.
Okay.
That's like the mindset. Once you keep that framework in your mind, you'll really, yes, you have it there, but like try to like explain like reality or physics out there. It's like, oh, if something is there's a physical event that happens, is that like a irreversible event? Can that happen? Like, and you could relate it back to like Newton's law. If it's in equilibrium, and then that gives free energy, does that mean that's equilibrium? Like, does it? You could use these definitions to explain not just what we're talking about right now, but like other things, and that's what's so great about it.
Mm-hmm. And okay.
And I guess for T10, are there I didn't actually take a look at that one, but are there exercises long? I haven't taken a look at it. Let me see.
Let's see. Exercise. I mean, it's just 2 questions for exercises, which it's asking if you consider a sample of calcium oxide at 298 Kelvin in 1 atmosphere of standard conditions, does the Gibbs energy of the sample increase, decrease, or remain constant if the temperature is raised to 350 Kelvin at 1 atmosphere? And then, does the Gibbs energy of the original sample increase, decrease, or remain constant if the pressure is doubled at the same temperature?
Okay, I think we can answer those ones.
Okay.
Though that one isn't that bad. I think I should be able to get you those. The critical thinking, they usually take a long time, but your professor's already giving you the answers, yeah.
For the most part, but he kind of sums it up, so it's kind of like a, for the most part I can get it, but some of them I miss.
Yeah, once you get the solutions to like this one, let's try. Maybe we can go over those.
Okay. The solutions to T9.
Every one of them, okay. So because like it's kind of, I don't know if he's gonna keep his like deadlines consistent, but if he does it that way, then like I could always give you the exercises like during this time, and then he gives that to you guys tomorrow. Does he usually give it to like on the day of?
So he generally gives the solutions, which includes exercises and critical thinking problems, usually the day after they're
day
due.
After. Okay.
So
yeah, that's perfect. That's gonna be that Thursday. It's gonna be a Thursday.
Okay, yeah, it looks like T10's the second exercise is pretty intensive. So they're showing a setup where it's like a membrane. It almost looks like an osmosis type problem, but temperature is constant. You have hydrogen gas on the left side, but on the right side of the membrane is a mixture of hydrogen and nitrogen. And they're asking for the relationship of mu pure to absolute mu when
Okay.
the pressure of hydrogen pure is equal to 1 bar. And then they're
Yeah.
saying which side is the free energy of hydrogen the lowest and which direction will the gas flow. Um,
Oh, that's a good question. What direction it will flow? Yeah, that's another
yeah.
practical one.
And then when you lower the pressure on the pure side, but raise the pressure on the or on the mixed side, um,
Yeah.
what side will the free energy be lower and what direction will the flow be? So
See, like a lot of these questions is really like, what is the sign, and and it tells you direction, right? Like
yeah,
direction of process.
okay, this is really short too because then next week the other topic is like 1 page Euler's criterion. It's just exercises. That's it. There's
Okay.
no
We, I think that'll be good. Maybe we can cover because you have that math exam, right? The math
uh
exam that's coming up.
yeah, the math exam as well as the chem exam in the same week. So
Oh, it's in the same week.
yeah,
Is
and
it?
then I
Okay.
think the week after I have the other class that I'm not getting tutoring for math methods.
Okay. I'm thinking like, but which one is the first one exam is gonna be the math one? Well. Oh yeah. I sent you something. Were you? I remember talking about the math. I'll give you the solutions for 6, like sometime like tomorrow or the following day. But then like, were you able to look up like problems that you were having a hard time on?
T9.
Besides like definitions, like or not definition, but like classifications of like differential equations.
Oh,
Yeah, were there ones that you felt iffy about, and so that I can prepare something on Thursday? Is what I'm saying.
okay. Yeah, that's weird. Let me see.
What
Oh,
happened?
okay. You did send me something. Okay, send me anything from those
Oh no, yeah,
problems.
no worries. It's not something you have to do right now, but like, if
Okay.
you have time, like, because like I'm I'm hoping you're already studying for the math one. That's like coming up soon.
Yeah, because the thing is that it's like stressing me out because hasn't given a specific day for when it's going to be. He still says it's going to be sometime next week.
Oh, he didn't figure. You sent me a text that was on the 12th. That's not the case.
Let me see which one that was. I get these two classes mixed up. So it'll be during the week of October 12th. It won't be on the 12th. It will be
I see.
sometime that week.
Okay, I'm hoping that's not the same day as the other guy.
Yeah, I mentioned to him about that, and he said, "Okay, I'll put that into consideration for it." So I hope
Okay,
it's
that's
not
good.
because
I I, I,
I
re-
have to travel and it's too much.
I really hate the fact like your professors are, they're probably really flexible, or like some of the ones that I had before were like very like, oh, final has to be on this day, and then like
Oh,
midterm,
finals are still going to be like scheduled, but these exams and stuff,
the midterms, yeah.
yeah, aren't going to be like super strict on stuff, so they can kind of move stuff around. But for the most part, it's just kind of it's just the difficult parts, the finals for
Okay,
figuring out the tones. Okay, let's see. So
so like I was thinking for this, I think we're pretty much done with the exercises, right?
for the exercises for T9, yeah, but I think yeah, I remember he went over a bunch of stuff, but I kind of got overwhelmed, and so I gotta rewatch the video to finish the rest of T9.
Yeah. Okay. Just send me the like the I guess the questions, and then or the ones that you feel like you need an answer on,
Okay,
and then like I'll be able to like maybe jump on that before tomorrow, and then I'll send you the homework 6, and if there's anything that like when you start studying on your like math exam, uh if there's something there from quick like the other stuff that we didn't cover,
okay,
I can write like some like I can cover that again on Thursday ahead of time. I can give you that and then we'll cover it.
okay. Sounds good.
Because I'm thinking like for Thursday we should definitely just cover math like fully,
Yeah.
and then like maybe Sunday we'll cover like the chem exam,
Okay.
like problems from chem, and then T10.
Yeah, it's just it's such a stressful thing because um
I know.
usually I'm like able to, I
Process.
guess, de-stress or process stuff, but like not right now because usually I I like to go outdoors and like metal detect
Yeah, I know.
on
I
the
know.
yeah.
What
And
what 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 I do sometimes to like get de-stress. It's kind of
yeah.
funny, but I guess because like when I try to just binge watch movies. So
Mm,
when you do that, like, or if you have like an outdoor thing out in the backyard, then you do something to de-stress. I know it's
mm.
like really stressful right now.
Yeah, so I'm just trying to get in something every week. But yeah, it's like it's tough. Because
Yeah.
like, people are like, "Oh man, let's play some video games." But for me, it's like, "No, I can't do that because video games take too much thinking." And so it's
They
like,
take time. They take time. Like when I
yeah.
used to play video games, like you'll say you're gonna be playing for like an hour, but it turns into 6 hours.
Mhm. Yeah, it's just like for me, like I overanalyze everything, and so I'm like
No, that's
I'm
good. That's good. That's good.
extremely strategic. But I don't like strategy games. But like even like
RPG games.
FPSs and things, like I'll just like try to think too much about like the best way to,
Strategy.
yeah.
Yeah.
And so because of that, it
Takes
takes a
too
lot of
long.
brain power. So yeah, I always feel drained when I finish, even though it's
That's
supposed to
funny
be
because
relaxing.
that's a de-stressor event.
Yeah, I don't know why, it just comes down to just me just staring into space or taking a nap or something to take a break.
Yeah, it's all good. Yeah, maybe just do
Yeah.
that. Whatever works. Like for me, like I said, I binge watch like shows, and then I go outside to like, oh, I exercise. That's another thing.
Oh yes.
If you exercise, it's like a stress reliever, obviously,
Hmm.
and then like you can go back. You can go back to whatever you're doing.
Yeah, and especially because I love colder weather, much more than
Okay.
hot weather, especially
Okay.
like when it's boiling hot. So right now it's starting to actually get colder, and so it feels real nice to be out. So probably.
Man, I'm the total opposite.
Oh
I
man, but
guess.
like you're in California, right?
Yeah, like love
Like,
hot weather. Yeah.
yeah. How are the fires? Are you in
Okay.
an
Good.
okay
Good. Good.
area?
Yeah, I mean, if you're outside California, everyone thinks like California is like all on fire.
Oh no, it's just sections. I was just making sure like you're not in an area that's been like.
No, I'm actually in LA, but like how like they always say like LA and like what was it San Diego, they're prone, right? They're prone to
Mhm.
fire. Central, especially San Francisco. I don't know if you've been following like what happened in San Francisco, but like the whole orange, like they didn't even see the sun, right? The whole day was
Yeah.
dark, like it was like Mars, orange like Mars. So I was like, oh my goodness, like they were feeling that, but then all we had here in LA was like hazy,
Hazy.
yellowish
Yeah.
smoke. Yeah, not too bad for me. I
Yeah.
actually I like those kind of events. I don't know. I'm kind of like like that.
Mm.
Like I think an earthquake happened the other day, and like some people were freaking out, but
Yeah.
it's quite exciting, I think, like
Hmm.
having these natural events,
Yeah.
and like you experience them.
I like part of my family is Japanese, and so I've been to Japan
Oh,
multiple times, and yeah, almost every time there's an earthquake, and so it's
oh my, yeah,
surprising,
definitely,
but
yeah, in Japan,
it
yeah.
it's so common. It's just kind of, yeah, I guess that happened for the fifth time today.
Oh my, like, were you tracking? I don't know if did you have family when the Tohoku earthquake hit?
Yes, but I think we were actually not in the area that was hit. In fact, like we were visiting other family members in Hawaii, and we were actually in the air after like we were flying when that happened.
You were like literally flying while that happened.
Yeah.
Like, from
Mhm.
what? From Japan to?
I think from Japan back to Hawaii or something.
Oh my! Like, can you imagine? Like, what if like you're in the? I mean, this is just like in the runaway, and then it happened. No, no, no.
Yeah.
I'm just kidding. That's like Final Destination stuff.
Oh, yeah.
But yeah, like yeah, it was pretty bad. Like I actually helped out in the kind of like an effort for that to
Okay.
help out. It's yeah, like
It's
it's not
scary
exciting,
stuff though.
but like the whole earthquake and tsunami, the
Hmm.
earthquake and tsunami. I'm hoping they recovered their, you know, the power plants. They're all fixed now. I don't know what happened after. So.
Yeah, right now that area is still like there are still hot spots that you can't visit, but it's
Oh wow.
it's gotten a lot better. You can actually go to Fukushima now, but there are still
Fukushima, that was the
areas.
one. Yeah.
Yeah, there are still areas that are still radioactive, though not nearly as bad as like Chernobyl.
Chernobyl. Yep.
Uh, but some people who live there do have there are higher incidences of cancers, so it
Oh
definitely
my.
did leave a mark. um,
Okay.
but yeah, we're safe. My mom's safe, everyone's safe, so that's all.
Yeah, I'm just hoping like this year, nothing, you know, more, because like they were always saying like, okay, we had the wildfires, right? We had that what's it called? We had the volcanic eruption in like the
Mhm.
beginning in Philippines. There was like the
Yeah,
volcanic eruption in the beginning of the year. It's like everything's happening, like, you know,
yeah.
like, and then like the earthquake, maybe the next big earthquake that's gonna like make California drift.
Detaches.
Yeah.
um
So like, I'm hoping that doesn't happen. I think the highest earthquake I felt here was like a
a 7, wow.
7 point something. But
It's
yeah,
just a
it's pretty insane if you're like on
pain.
top. If you're on top of like a building, can you
Mhm.
imagine? Like,
Oh gosh, the swaying.
yeah, it's I mean, I don't think it was that severe, but
Okay.
it's just one of those things where you probably had you probably felt worse than what we felt here in California.
Yeah, and like two things I can think of. So I know in Japan, like I'm always amazed at the construction of the bridges and
Oh yes.
roads. Like they're like you can see heavy rivets and like
Yep.
really
Okay.
hard, heavy duty, almost looks like bucket pieces
Yeah, they're
um
pretty huge. Yeah.
of steel and things like that. Is
Yeah.
that common in your area
In California.
in California?
It's different. We don't call it rivets. I mean,
Or
in
bolts
essence, like,
or
yeah,
whatever?
bolts. Yeah, they're called bolts now. That used to be what it was before. Like, you know, when
Mhm.
they built something, like it's just the way that the process of doing that. Like, you just like molten, and then you just hit it. But
Yeah.
now, like, it's machinery.
Hmm.
For the most part, bolts here are in California. That's why I like being here, because the construction is actually at a
Oh,
higher
it's
level.
great.
That
Yeah.
and you know, you have the wildfires here, so you would think at the same time. That's why I feel like if you're in the, you know, in the middle of like all the disasters, maybe in people in like Florida,
Hmm.
if you're in the middle of like the high wind areas, you get to experience, and that's the reason why I kind of like it, because you get to experience like the fun, the design aspect, you know.
Yeah. It's
Like
fascinating. So are
the
things
consequence.
yeah, are things earthquake resistant in are the bridges and
Yes, yeah, there's
everything
ways to,
highways are earthquake resistant there?
yeah, a
Okay.
lot of it, it's probably kind of similar to Japan, right? Like,
Hmm.
because it's like very high, like earthquake zone or whatever, wildfire zone. You get to like, you can never design it if it's not seismic proof or it's not like wildfire proof. It's like the codes there versus the codes somewhere where it doesn't matter. All right, like, and that's, they're like, all the buildings are definitely more expensive to build, but in the end, yeah, they're more robust. They'll, and then they can sustain like higher loads, you know, stuff like
Yeah.
that.
Okay, let me see real quick because
Okay,
yeah.
do you I think we're pretty much done.
Yeah.
Do you want to just end this one and I'll just make it 1 hour?
Okay, that works.
Okay. Yeah, like whatever I said. We can meet and do that stuff. Kind of like I kind of just planned out the week. If you wanna, just let me know if there's other things you wanna like talk about.
Sure thing.
Okay.
I'll
All right,
let you
man.
know.
Andrew, have a good one.
All right, you too. Thank you.